Hello, everyone, and welcome to We Meet at Digital Days. My name is Marie-Therese Kohl, and I will moderate this presentation. We are very pleased that you took the time to participate in our virtual conference. The topic of this presentation is loop compensation in SMPS, example of bug with voltage mode control. Our speaker is Alain Lafuente. He will hold the presentation and will answer your questions. Before we start, I would like to point out one thing. You will be muted during the presentation. This means that you cannot ask questions via microphone during the presentations. Nevertheless, you have the opportunity to ask questions during the presentation at any time via the chat function. You will find the chat function in the control panel. This presentation will be about 30 minutes long. The chat questions will be answered in a Q&A session following the webinar. There are 5 to 10 minutes in addition scheduled for this. If we are unable to answer all your questions within this time, we will answer them via email afterwards. If you still have any other questions left, just mail us at exhibition@we-online.com. We will try to answer all questions promptly. At the end of the webinar, you will be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve the event. You will receive the link to the presentation in the next few days. The recording will be available at our website shortly. But now, I will hand over to our speaker Alain, and I wish you an exciting presentation.
Hi everyone, I hope everything is okay from your side. I'm pretty happy to share these topics with you because it's kind of tricky topics when we are designing power supply because there is a lack of information regarding how to compensate a power supply, every kind of topology. But today we will focus on buck converter because it's the easiest to design. And more than that, we will discuss about voltage mode control because as well it's the easiest to understand. And once done, you will be able to jump into some more difficult topic like optocoupler compensation and current mode control. But this is a kind of trilogy of Würth Elektronik topics because we have 3 different presentation covering every part. And let's go with the first one. So as my colleagues told you, if you have any question, feel free to ask. If you want with the chat by mail, for people having my phone number by phone, by email, whatever, send me a bird if you want. So first, if we don't copy and paste just application note from IC manufacturers, just because our specification is a little bit far from application note, so we have to make our own design. So we will start. I will check my pointers. Yep, happy day. So let's start with the beginning. So we have to define at first IC. Your preferred IC manufacturers doesn't matter. IC part number. So you have to select the one that you want to use, you want to buy, and you know probably your selection is a trade-off in between price and the way to use it. Diode as well, and of course inductors and capacitors. Capacitors are at the output, at the input. I don't show filters here because this is just a copy and paste of filtering presentation. So you will know, or you know, that there is some parasitic elements such as inductance, coupling capacitors somewhere. So and you have to spend a lot of time making calculations. So for inductors, for instance, you have to make a trade-off in between what is good for my inductors and what is good for my application. Meaning, what is good for my inductors is, on magnetic point of view, how can I deal with ripple currents versus the size of inductors and the ability to the inductor to store energy. I don't want to have a big tank. I want to design or to size the inductance not so big and not too small, just to have a good trade-off. But in the other hand, I have also to deal with the ripple regarding my application. Let's say I have a RF module, so I assume that I don't like so much ripple currents. So my trade-off will be to reduce the ripple currents, and the tax to pay will be to increase the size of the inductors to store energy, blah, blah, blah. Capacitor as well, to control the ripple voltage at the output, let's say 1%, which is a regular target for power supply design. I can as well deal with transients. So maybe I will use different methods to calculate capacitance to deal with transients, output and input. So I can have I can spend a lot of time to do that. But this is the end of the calculation. I'm quite happy to make the calculation. I still have some noise because I didn't filter yet, and we don't do that today. But this is what I can see with simulation. This is my switch node with a lot of noise and quite big overshoot. And this is some kind of ripple voltage that I have at the output stage. That is a steady state. Steady state doesn't mean stable. Steady state means I provide input voltage, I want a given output voltage, and this is a steady state in between. But if I have a load transients, for instance, if I didn't pay attention to that, my power supply is not stable. It's everything but not stable. And this is just normal. And my idea behind this, I need to check what's happening in the output, what's happening in the input, to be able to react on a proper way if I'm facing to a transients. Could be load transient, could be input voltage behavior, whatever. But without any compensation, my power supply is everything but not stable. So the target of this presentation is to start with the simpler one, as the simplest one, and to see what's happened and how to understand the mechanical behind. So everything is linked to loop control, because if I take a look on the system, so this is my power supply working in steady states. And if I have kind of disturbance of variation to the output or input, I need to add a block to be able to check in real time what's happened, as this is a feedback control system. And the fun is my system must react not too fast, not too slow. And behind that, we can add with a good safety margin, phase margin and gain margin, to be sure that we will be stable. But it's not clear, because what does mean not too fast? What does mean not too slow? I don't know. Maybe I'm French, so I can speak a lot. I can say everything, and I can speak prior thinking as well. And this is typically what is a feedback control system. So is totally unclear to say not too fast, not too slow. So we need to go into deep details to have a clear idea what means, what is the meaning of that. So let's go. First, my open loop, because my open loop is here. This is the denominator. So there is a forbidden point for my open loop, and my open loop does not cross -1. So meaning 1 in amplitude and -180 degrees in phase. So that's its Bud plot and Nyquist plot in this side. So what does it mean? Once I'm going to 0, I can't, or it's forbidden to reach in the meantime -185 degrees, because my system will blow up. My system will blow up because my denominators will reach infinity. So this is a forbidden state. So this is Bud and this is Nyquist. So you can have, if you prefer this one or this one. So I need to provide phase margin, because once my gain cross 0, I need to have a sufficient phase margin to avoid to reach -180 degrees. So that's defined by phase margin. How much? That will be the speech a little bit later on. And in this case as well, you will see -1 point, and I will have phase margin. Gain margin, it's exactly the same thing. If my phase reach -180 degrees, I need to be sure that I have enough gain margin to avoid to cross 0 dB. So this is a gain margin and this is a phase margin. And how to understand that and how to decide what is a good phase margin or a good gain margin, and this is the following. Every kind of system, at least in electronic, we can speak about second order systems, because sooner or later I will have some dominant pole somewhere, even if I speak about of third orders, fourth order, fifth orders, no matters. At a given moment, at a given frequency, I will react like a second order. So second order, it's looking like that. And I can link time and frequency to see the behaviors in time domain, or in frequency domain. So I can see in this case, this is a second order system. If I don't damp the system, my answer will be, or my response to a step, for instance, my response will be fast, for sure, because my rest time is very fast. But the tax to pay will be to have a bump in somehow, because I can have more than one bump, overshoot, undershoot, and I have to think about the settling time. So at which moments my response will reach my input or my signal. So this is a settling time. How many time I need to reach if I want to go to 5 volts? How many time do I have to spend to go to this 5 volt? So I can be under than paid. I can be over than paid. All depends the response that I need into my system. So I can be very fast with dump. I can be fast with only one small bump and almost no under voltage. So that's just a trade-off in between what I want and the way that I want to react against a transient. And I can define, this is just pure math. We don't care a little bit right now, the mathematics. So this is just to show you that we can define everything with math because we know almost perfectly a system, and we can define the rise time, we can define the bump or every single bump that we can have with comparison to the numbers, so the first bump, the second, the third, and so on, and the settling time. We can define the settling time mathematically speaking, so we know exactly what's happened. And this is exactly the same case because we can shift from time domain to frequency domain. Everything is linked. So we can define overshoot, we can define quality factors, and we can define cutoff frequency. We can define everything just using mathematics. And the last point is faster my response, higher my quality factors. And faster is a shift in phase. And we don't like to have a very fast shift in phase because it's quite difficult to control and to compensate and to handle. We like to have something smooth. So the target is to be right in between here, not too fast, not too slow. Too slow means too much time, too fast means too much difficult to handle, plus oscillation, smooth oscillation. So this is not something interesting. Other point is we need to reach the target soon enough, and this is the mix in between. I'm too slow in this part, so I will reach maybe sooner or later my target, but maybe I will need 1 day or 2 days to reach it. So this is forbidden. I can reach it very fast, but there is instability in here because I have too much overshoot, undershoot, and this is not acceptable because, for instance, my power supply can have some problem with over voltage limit, under voltage limit, so I can turn off my power supply just because my swing is it's too high. And right in the middle, it's not too slow, not too fast. It's fast enough. I can deal with one overshoot and maybe a small undershoot, acceptable in between a given limit. And the time to reach the target, it's short enough. All depend on my system behind my power supply. Is it processors speeding a lot? Is this just a more simple system? So target is to react fast enough. it's not necessary to react as fast as possible. It's just I just need to react fast enough. Other points, I need to be precise. So I need, if I want to reach 5 volt, I need to kill or to cancel a static error. Means if I want 5 volt, I will have 5 volt and not 4.7 or 4.6 volt because I have a static error. I need to react fast enough if there is a change. And acceleration is not the job of power supply, but if I speak about plane or something like that, and if I have a loop compensation, of course, I need as well to take into consideration acceleration, but not in power supply. Power supply, static error and speed, it's more than enough for us. Piece of math just to show you the limit of system and which type of system I will have to use. If I check the static error for a first order system, so what is the response of a step? I will see that for a first order, I will have a static error. And I can't change that except in changing the gain. And I can't have infinity gain, so I will still have static error. So first order system is not a good choice. If I take a look on velocity, this is Laplace transform. So I will see that I will have infinite error. So still not good. So if I summarize, first order, second order, third order system, I see that a second order system will give me zero static error. Velocity, quite enough. Acceleration, not my business. Third system will be better, but for electronic doesn't make sense. So if I translate in electronics, what I need to do if I compensate, I need to cancel or to minimize as much as possible the static error. How to do that? Hedging, eigen at low frequency. I need to define the speed of the reaction in selecting the crossover frequency, meaning the frequency where my gain cross zero. That's the meaning. And higher the crossover frequency, faster my system is. Faster my system is, more dangerous because I will have oscillation. So that's the trade-off. And set the phase margin, it's the deal in between the crossover frequency numbers, so the value of the crossover frequency, and the way that my system reacts. Higher the phase margin, I can compare a very high phase margin with a first order system. So no oscillation, but a settling time quite high. So that's the target. So if I take a look on buck converter, and if I plot the transfer function of a buck converters, this is the plane or the direct chain. There is plenty of words defining the transfer function. So meaning my MOSFET or my IC and the gain coming from my IC and the output filters of the buck output filter. This is L and C at the output of the buck converter. So if I plot this one, I will have a gain given by that double pole given by the resonance of the LC filters. I will have minus 40 dBs per decade because this is a double pole. And I will have the zero of my capacitors coming into the game and reducing because it's a zero. So I add plus 20 dB per decade. So minus 40 plus 20, this is minus 20 degrees attenuation or roll off for my gain. So that's what I have. This is a direct planes transfer function. And what I want is to select a speed and to select phase margin and gain margin. So I need to add my compensators to select the speed, static error, robustness, of course, because I have to pay attention to aging, to temperatures, to a lot of things. So I need to be aware about that. Compensators could be with operational amplifiers, like such kind here. I can have, if I need isolation, I can put a TL something or TLV something, shunt regulators plus optocouplers, or I can use transconductance amplifiers. So for today, we will use operational amplifiers to set compensator stage. So what I need to know or what I need to do is I need to be far enough from my critical point. So I need a little bit to increase the gain for static errors. I need to increase phase margin to shift my path or to have some safety room. And as well, I need to increase or to set the gain to be sure that when the phase is reaching or not minus 180 degrees, I will be far away from this point. So back to my transfer function. So I need to have high gain at low frequency, kind of polar at origin, and we will see later. So I need to increase the gain here. I need to cancel out my double poles because I have a fast shift in frequency, in phase, and I have a minus 40 dBs per decade, which is too fast. So I don't want that. And I have as well my zero coming into the game. So my target is to have something at minus 20 dBs per decade everywhere. So from low frequency, this is integrators, this is high gain at low frequency. I need to cancel out my double pole to still have 20 dBs, minus 20 dBs per decade. And I need to cancel out ESR0 to still have minus 20 dB per decade. That's the target to be sure everything is okay. So I have a lot of different way to do that. All depends the phase margin that I want to use. If I use a type 2, this is not second or third order. This is totally different, but could be a misunderstanding. Phase 2 means one pole and 1 0 plus a pole at origin. So my integrators at low frequency, minus 20 dB per decade. I add a 0, minus plus 20, 0, and I add a second pole, minus 20. And the target is, this is the boost, and this is the phase merging that I will apply to my system. And for a type 2, the boost in phase, it's not more than 90 degrees theoretically. So in real life, uh, not more 70 or 60, to take into account aging, tolerances, temperature, and so on. If I need more, I can go with type 3, 2-pole, 2-0 plus pole at origin. So pole at origin, 1-0, 2-0, 1 pole, 2 pole. And the boosts available, it's 180 degrees as well, theoretically speaking. So let's go a little bit more fast because the time is running. So for my presentation, I will use 201 pole. Why? Just because it's my presentation. And just because 20 to cancel LC filters, and 1 pole to cancel ESR0, and 1 pole at origin. So that could be something like that. And the idea at the end, it's to cancel out, which is done. This is LT Spice simulation by the way, so this is right in here. So my 0, it's placed a little bit below and a little bit above my resonant frequency of LC filters. This is a pole at origin, and the second pole is placed to cancel out ESR0. So I will have looking like a filter 0, and phase merging in that case, it's a little bit high. In that case, it's 86 degrees phase merging. So for sure, my system, if I take a look, it's quite good. So internally, what's happened internally, if I take a look on the IC, because everything hidden in the IC, it's unknown or not know perfectly. So what's happened when I take a look inside an IC? So my compensator stage, my compensations, and my system to set as a duty cycle. And this is a bridge divider. So most of the time I can have only this kind of component outside. So what's happened inside the IC? So I have error amplifier. So depending the swing of my output voltage, I will generate a signal error. This signal error is compared to a ramp, and as soon as my error is equal to the ramp, I will shift my duty cycle to be able, with a fixed clock, to be able to change my duty cycle. And this is a duty cycle. If transient arise, what's happened? My voltage error will be changed because I have undershoot and over voltage on the output voltage. So automatically my error will follow output voltage. So means my voltage error doesn't cross ramp comparators at the same place. So I can change duty cycle to react against this transient, or this this slot transition. So I can reduce or increase my duty cycle to try to react fast enough against this transient. And this is what's happened with output voltage. This is internal process, and this is what I measure at the output. Am I happy or not with these transients? That's the target of the design. Does this undershoot is too high? Does the setting time or the response time is too slow? That's the target of the design. If I answer yes, it's too high or it's too slow, I need to change a little bit the thing. So how to change the fact is who is responsible of that? If I don't want to change anymore the loop, inductors is not involved into the game at all. It's not necessary to change inductance or to say inductance doesn't work well. Inductors doesn't work in this game at all. The only components working in it is the output caps. I can change the value of the output cap, sorry, to change a little bit the slope here or the waveform here. I can check ESR because that's undershoot, this huge undershoot. It's mainly given by ESR of the capacitors. So I can try to reduce it to change it. That's a way to do. And if I do that in such a way, I'm changing a little bit capacitance value. Not so much because don't forget, transfer function include ESR0. So includes the behavior of the capacitor. So if I change a lot, my compensation must be changed as well. So that's really important. So I can reduce ESR to reduce the undershoot and to have recovery time acceptable for my application. This is what's happened here because we had 4.80 something volts on the previous slide, and in that case we have 4.94 volts. So this is for simulation really acceptable. Last point prior to stop, because I'm 7 minutes late, but don't forget I'm French, so this is a normal time for me. 50 minutes late in French is quite okay. So what's happened if from continuous mode I shift to discontinuous mode because I made a mistake. I didn't make calculation with the right light load, and I reach at a given moment discontinuous mode. So what's happened? In orange, this is the transfer function in discontinuous mode. So I will see immediately in Excel sheet. Phase is not a problem at all. But my transfer function in discontinuous mode presents a crossover much more lower than the crossover for the continuous mode. So if for any reason I fall in discontinuous mode, means transient response will be lower. Is that a big deal or is that a problem? That's an open question for the application. But for sure, this is still a LT Spice simulation, but this is for sure that in discontinuous mode, my recovery time will be much more longer than in continuous mode. So, and if I'm very not lucky, I could go into instability, but most of the time, the tax to pay if I change in between continuous to discontinuous will be higher recovery time. If it's a problem, so I have to rework my inductance value to set the critical point in between discontinuous and continuous, and so on and so on and so on. So that is the end of this short introduction of loop compensation. Next time we will speak about optocoupler And next time after, we will speak about current mode, much more funny. If you have questions, comments, feel free to use. I will try to open the question.
Yeah, thanks, Allah, for your interesting presentation. As you already mentioned, we would like to turn now our attention to your questions, and we will wait a little while until some questions have come in. But I can already see that we have one first question. How the frequency response of the bug has been simulated on LT-SPICE using a small signal model.
No, not for voltage mode. For this particular voltage mode, I just make the simulation changing sorry, changing a compensator stage, which is operational amplifier, just with a voltage to voltage source and putting gain in between. I didn't use voltage mode, except at the end for the comparison in between continuous and discontinuous mode. Yes, I used AC simulation models. Yes.
Okay, thanks a lot. So I would say regarding the time, if there are any questions left, we will answer them via email afterwards. But thank
Can
you
you
very
share?
much.
Can you share your LT Spice file? Yes, of course. There is nothing secret. This is just a LT Spice simulation. So yes, I can. I will give
Cool.
to to
Perfect.
uh, to you. I will send everything to you.
Perfect. So, thank you very much for your attention, and I hope you enjoyed the presentation. The next presentation topic is how to increase efficiency in NFC RFID systems with magnetic shielding. It will start at 3 p.m. So see you there and enjoy our digital days. Goodbye.